Hey, you 13s! Hello! So, we've got Transition Metal Aqueous Chemistry Part 3. I think this is Part 3. So today we're going to be looking at chromium. And what we're going to do is, the great thing is, you see, this is going to reinforce each time we do a transition metal. So today we're going to be looking... Sorry, get rid of that. Save my CPU. Get rid of that. I've got my little popped out chat window. Yeah, get rid of that bad boy. Okay, now what I'm going to do is I'm going to share my screen. I've suddenly realized I should have copy and pasted the learning objectives. Damn. Okay. I might actually still be able to do that. I can. Amazing. Control C. Winner. Share screen. Oh, no. That one. And then I then go to my notes. That was the end of my acid-base lesson. Running right to the wire. So we've now got, this is transition metal chemistry, PM aqueous chemistry. Just let me write there. Oh, it's not letting me write there. Ah, there we go. TM aqueous chem, lesson 3, chromium. Chromium. Sorry, guys, not as set up as I'd like to have been. Right, so 3 learning objectives, guys. Bonjour. Funny. Right, cool. So we're in. So I hope you guys had an opportunity to watch that, the YouTube video that I posted on the classroom of the guy doing the copper ones. They're really nice. Just want to quickly mention that copper lesson. When we get to the, now I've actually set you guys a homework now on copper, and I just want you guys to realize that copper does have one additional color, and of course, well, actually technically 2 additional colors, but one of them is not really a color. So if you can add this to your previous notes, yeah, and we've actually already done this. We did this in our complex lesson, yeah. So the other copper colors, yeah, other colors. The other colors for copper is CuCl42-. And this is yellow. This is yellow, by the way. This is actual color. The actual color is yellow. However, often observed as green. Green observational, not observational, but observational. The reason being is trying to get the equilibrium to swing right over to the yellow is really tough, and it tends to be mixed with the aqueous blue as well, giving a green color. So just to mention one more, CuCl43-. This does exist, and it is colorless. Yeah, the reason why this is colorless is because the copper in this one is an oxidation state of +1. Oxy state here is copper +1, and copper +1 has a full D subshell, so it is going to be colorless. It's nice just to mention those extras. So the true color, it's nice just to add a bit of color to my notes. The true color of this guy is yellow, but the observational color is often seen as green, and they will usually allow both colors in the exam, which is nice. Okay, so today's lesson is chromium. Now I'm going to take this approach. I'm going to take this from a slightly different approach. Oh, I've lost my. Oh no. Oh, there we go. There we go. It's my title. I thought I lost my title. Now, I'm just going to use each lesson. I'm going to remind you of the table. Yeah, because when we're learning colors, when the teacher first says to A-level students, there are over 50 colors for you to learn. Yeah, this is a nightmare because everyone panics, and you shouldn't. We now have copper. So copper's colors are blue, 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 blue. Hang on a minute. Blue. So this is the hexaaqua. Blue, 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 dark blue. Is that right? No. Dark blue is now 4 blues, then a dark blue, then a blue-green. Yeah, there we go. And then you just have your others, your oddities of yellow. Yeah, those are the ones that you need for copper. Oh, I'm just going to add a couple of other ones. Oh, no, extra oddities for copper. Sorry, guys, extra oddities. You also need to know copper oxide, which is a solid, is black. You need to know that guy is black. Yeah, that's important as well. And copper metal itself, by the way, pure copper metal is pink. So you can add that one to your notes as well as an oddity. Yellow, CuCl42-, and then, of course, your black CuO. There we go. So these colors come from the fact that we have the hexaaqua ion. That's the hexaaqua. This is a little sodium hydroxide. This is excess sodium hydroxide. This is a little ammonia, and the littles are always the same on all the tables, which is absolutely amazing. Then we have excess ammonia, by the way, usually concentrated, conc, and then followed by carbonate ions. So these are the color table that you learn, 6 colors. So we go blue, 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 dark blue, blue, green, blue for copper. So you learn them in a string, yeah? And if you learn them as a string of colors, it's easier to remember the colors. I hope that makes sense. Now we need to look at this from chromium's perspective. Okay, so chromium. Now I'm actually going to do this in a slightly different fashion. I'm going to do this like this, yeah? So we love chromium metal. Yeah, so let's actually pick, so we're going to look at chromium today. Now, the first thing I want to do is just talk to you guys a little bit about, because we talked about the dehydrated, the anhydrous salts. One of the key things that students often forget is that if you have a transition metal salt, such as chromium sulfate, so the example here, I'm going to shrink my pen actually. I do want to try and keep my writing all of a similar size. So chromium 3 sulfate. By the way, yeah, chromium 3 plus is what we're actually talking about here, guys. Sorry, you can add that to your notes. It's actually chromium 3 plus we're talking about. So first things first, the anhydrous salts, let's do chromium 3 sulfate. There we go, are going to be white. These guys are colorless, but as a solid, it's definitely going to be white. Yeah, I'm going to add this with some form of a gray. That looks like I'm trying to aim for, yeah, let's go for white. Oh, can't do that. I need a highlighter, which is pale, really thick. There we go. So we can just put observation, that's a white solid. White solid. There we go. Okay, now what we're going to do is we're going to take that white solid and we're going to add water. So what that means is we're going to form our very first complex of chromium 3 plus with a color. So what we're going to now get is we're now going to add water. I'm just going to go add H2O, and the salt dissolves, and I now form the chromium hexaaqua chromium 3 plus complex. Hexaaqua chromium 3. And it does indeed have a color, and its color is violet. Yes, that's right, it's violet. I'm sorry about that, guys. It's like, but here's the thing is you're not, darn it, I've done it again. You're not allowed to call this purple. I'm very sorry. Yeah, it's violet in color. Now, they actually accept loads and loads of different answers. This is actually the observational color. Now, students always hate this idea of observational versus reality and all this jazz, and it's a bit of a nightmare. And in reality, guys, you just have to learn the observational. In my day, we had to know both, not so much anymore. Now, just to let you know that if you were going to take this complex and do theoretical color, the theoretical color is ruby red. Ruby red, which is actually about like that. Yep, that's about right. So the theory color is ruby red. It's ruby. Yeah. But then we get these observationals. Yeah, observational is violet. But the annoying thing about all of this, yeah, so that's violet, observational. There are other colors you may see. Another example is if in the presence of an alcohol, it'll be green, observational green color. And it's about that kind of green. So this is another color that they allow. Yeah, and this is in the presence of alcohol. In presence of alcohol. Now, this is one that you have to know because this is the test for alcohols. To add potassium dichromate, and it'll turn green in the presence of an alcohol if it oxidizes it. And that's actually the reason why you're forming the hexaaqua. Just to let you know, the alcohol is probably acting as a ligand, and hence why you see an alternative color in the presence of an alcohol. But if they ask you for the complex causing the color, you actually still give the hexaaqua, which is the nightmare. So chromium has got a whole load of problems with it that come with it. Right, now what we're going to do is we're going to follow our table. We're now going to take that violet solution and we're going to add a small amount of NaOH, little sodium hydroxide. I'm going to try and keep all the writing to one side, I think. We're going to add a small amount, a few drops, by the way. We're going to add a few drops of sodium hydroxide. And what's going to happen? So let's go to my things. Let's do chromium 3 sodium hydroxide. Now what happens is you're going to form a green precipitate. Images. I'm kind of hoping there's going to be a picture of the real life thing. There you go. It's gross or what? So you form the violet color, which it started out as, forms a green precipitate. So, and now what we now need to do is now need to look at the equation. So the chromium hexaaqua 3+ is going to act as an acid. Yeah, sorry about the square brackets. I'm going to try and improve those. Yeah, the chromium aqua 3+ is going to act as an acid, and it's going to react with hydroxide ions. And the question is, on the chat, how many hydroxide ions is it going to react with? Wonder how many people are going to figure it out. Don't know how many people are still in the chat. Thank you very much. 3 is the right answer, Tanzi. Well done. In the little ones, that will always match. Yeah. So we're going to end up with that scenario. And there is our green precipitate. Remember, any precipitates, Julian, it wasn't 2. No. It's going to react with 3 because it's going to attract 3 OH minuses to it. Plus 3 will attract 3 1 minuses. Yeah, and there's our precipitate. Remember, all neutral precipitates, reinforcement from the copper lesson, all neutral PPTs are neutral complexes are PPTs, are solids. So we actually now form a solid pale green, just need green, by the way, looks like that, a green PPT. I'm going to switch to my black pen. And this is the chromium triaqua trihydroxy complex. And the great thing is, it's easy to remember because you always cancel out the charge. The number of OHs over here, this number here, is always going to match the number that was charged on the original complex. Loads of links and connections that we make at this stage, guys. Okay. Excuse me. Next one. We're now going to add excess sodium hydroxide. So we're now going to add excess OH minus. So what's going to happen now? Let's go to the pictures over here. Right. So when you add excess, this is where this is going to be a bit of a nightmare as to trying to see this. There we go. There we go. Perfect. That's the picture. It's got them all there. Right. So we start off with the original. Oh, no. I didn't want that. I didn't want that. Didn't want the YouTube video. Get rid of it. No. No. I just want the picture. There. No. Just let me zoom in. Oh, no. No. I'm sorry, guys. Hang on. Yeah. So the first one, the hexaaqua actually isn't here in this particular scenario. Yeah, but the first one here, there's the green precipitate, this sludge at the top, and then it disappears. Yeah, they haven't actually done it in the right sequence, just so you know. Yeah, they've done that in the wrong order. So what's now going to happen is, now because chromium 3+, because the hexaaqua chromium 3+ is more acidic, yeah, we know that the 3+ have a pH of 3, whereas the 2+, like copper, are pH 5. This is way more acidic. Now, what that means is it's going to react with more sodium hydroxide. Yeah, so when we add excess NaOH, what now happens is it reacts with all 6. And what now happens is we now form the hexahydroxy chromium 3+ or chromium 3 complex. It's not the reason why I don't like saying the word plus. Now, can I just point out, this is not ligand substitution. This is Lewis acid base. No, this is Bronsted-Lowry acid base because it's proton transfer. Remember that the OH minus in the diagram, the OH minus is removing a proton. It is doing this. This is what, the OH minus ion does this. It's stealing a proton and not as a ligand. It's not doing that. Yeah, this one here is incorrect. Yeah, it's acting as a base. This is a BL base, a Bronsted-Lowry base, a proton acceptor. Yeah, so it's actually going full, it's giving away every single, now this is actually quite unusual. There aren't many of them that actually do a full removal of all protons, but chromium is one of them. Now what this means now is my complex now has an overall charge. Now if it has an overall charge, guess what I'm going to be? Going to be aqueous. Yeah, so because it has a charge, it now redissolves on excess. So we now form the hexahydroxy chromium 3 complex. Now please note, it is actually still green. It's still green, but now all of a sudden it disappears. This redissolves. Instead of being a solid, it's now aqueous. Right. So we've done the little OH minuses and excess OH minus sodium hydroxide. Now we need to drop into the ammonia side. So now we're going to do little ammonia. I'm going to make that line longer. Yeah, little ammonia. Now the great thing is the littles are always the same. I'm tempted to move it up. No, that'll do. The littles are always linked together. Yeah, these two are the same. The reason being is that the ammonia is acting in exactly the same fashion as the sodium hydroxide was. The chromium hexaaqua ion is reacting with the ammonia and it's acting as a base in the little scenario. Yeah, it's acting as a base. And what's going to happen is that I'm going to have, triaqua, trihydroxy. What? I'm going to be my same green precipitate. But this time, instead of having H2O spat out on the other side, I now have NH4+, and I have 3 of them. Just to show you what's happening, yeah, the chromium has its water attached to it. Ammonia is pH 11. It's going to act as a base preferentially rather than a ligand. It's going to do that first. Yeah, so it's going to take a proton. And then that line there would roll back, forming an O-, which is where the charge disappears from. But it's nice to see what it's doing. So it's acting, these two are the same because they're both acting as bases. Now what this means is I have the same complex and the same color. This is great. So I have chromium, triaqua, trihydroxy. Learn the patterns more than anything else. It's a solid and it's green. Right. Now we're going to add excess. Right. Excess ammonia. And of course it's going to go in the form of concentrated. Yeah. Right. So unlike copper, now copper did something really weird. Yeah. Copper did a very odd change where instead of having, when it had all waters here, water, yeah, when you reacted it with excess ammonia or conc ammonia, you got a really bizarre outcome. The waters on top and bottom were left and the ammonias subbed in around the middle. Yeah, it was a rather unusual one. Yeah, in fact, it's very unusual. There we go. So they sub in and water's left at the top. These are just waters. They're the same as what they were before. The waters are left. And this was our dark blue solution. Now, chromium doesn't do this. Chromium is far more straightforward. Chromium really likes its full swap outs. Yeah? So what we actually get for chromium is that every single one of the waters is kicked out. All of them. So they're actually going to go complete substitution. And we're going to form a purple solution. Yeah, see, small amount excess. So we form a full swap out. Cu, NH3, ammonia, but I've now got, so this is the hexaamine with a double M for ammonia, 3+. We know it's a 3+ because ammonia is neutral. Now that one, of course, has a charge, so it's aqueous. And now we see purple. It's darker than the original purple, just so you know. It's genuinely, it's a darker purple. See if I can find a darker purple. The purple's more like that. Yeah, it's quite a nice purple, actually. And this one you actually call purple. The original one we call violet. That one there is violet. And this one here is purple. So it's a purple solution. Okay. So the next thing, the last one in the table is we're now going to add carbonate ions. Yeah. Now, by the way, just to show you the equation for the full swap out. So we've got Cu hexaaqua. Now, just to tell you, by the way, that you shouldn't really start off hexaaqua, but they do allow it. So do 6 ammonias. And we're going to get full swap out Cu NH3 6, 3+, and 6 H2Os. And we form our beautiful purple aqueous solution of the hexaaqua chromium 3 complex. Now, carbonate ions. We've talked about this in the copper lesson. Just a reminder, a recap from the copper lesson, from lesson 2. Tm2+ ions always form the carbonate, TmCO3. They just join on. So the example is Cu2+ plus the carbonate ion will simply form CuCO3. Blue-green. However, the transition metals with a +3 are more acidic. Yeah, they're more acidic, pH 3, compared to the pH 5 on the transition metal 2+. These guys don't bind to the carbonate, they shred it. What's going to happen is the CO3, 2- ion is going to get turned into carbon dioxide. And it's going to do that by providing its H+. So the overall equation that we're going to get, just to show you this now, the overall equation is chromium 3, everything starts off hexaaqua. 3+, pH 3, very acidic, reacts with a carbonate ion. The carbonate is going to become CO2. Now it does this by this providing protons. Yeah, and what that means is I'm also going to therefore water, because the oxygen that was in the CO3 2- is now gained H+. Now, how many will it lose? It's going to lose 3. It's going to form the precipitate that we saw on the other littles. There we go. And that's a green precipitate. And then we have to balance it, which I always hate. So this is lost, by the way, this has lost 3 protons, but 2 of the protons have gone into water. The common denominator is 6. So we need to multiply all this up like that, and then that, I believe. I think that adds up. So there's the equation. Can I just point out learning that has value? Because it's a nightmare trying to build it. I hate building these equations. I do build it, but it's almost easier just to flat out learn it. But the great thing is all the 3+ form the same thing. They form, shouldn't do copper, chromium. We're forming the triaqua, again, triaqua trihydroxy complex, which is a green precipitate, which is cool. Green solid. Cool. So that brings us to the end of the 6 colors in the table for chromium 3+. Now what we need to do is talk about chromium's oddities. So this is our oddities table. Oddities for chromium. And yes, it has a few. So first one, the dichromate ion. You've been learning this, guys, since AS. This one is my favorite compound in terms of color-wise. It is highlighter orange. Love the dichromate ion. It's beautiful. Potassium dichromate, bright orange. Next one. We then have the chromate ion, CrO4 2-. Yeah, this one is not orange, but in fact, yellow. Got to know that one, I'm afraid. Next, chromium 2+. Chromium 2+ as a hexaaqua. The hexaaqua chromium 2 is blue. And it's a blue solution. It's kind of a pale blue. It's not that kind of dark. What kind of a blue is it? It's a bit like that kind of blue. There we go. That's the blue it is. There we go. Any others for chromium? I do not think so. So I think that gives us all the colors you require for chromium. You don't have any oxides to learn. It's all good. No, that's it. Right. So now I'm just going to go back to my learning objectives. So number 1, know the colors. You've got to learn those, folks. You can't make them up. Number 2, write equations. We've gone through that. And the last one is this oxidizing and reducing agent. So, and it actually links into my oddities, because quite often we start off with chromium 3 in these kind of cycle questions you get. And what they want you to do is raise or lower oxidation number. So I'm just going to zoom. I'm just checking my writing's got really big. I'm going to have to sort that out. Okay. So can you just put a little subheading of oxidizing and reducing transition metals. Okay, and this is really straightforward. Now, you guys have been talking about oxidizing and reducing agents since you started AS, and so this is just a new one that you've got to add to your repertoire. Yeah, so if you wanted, let's say we start out, we're going to start out at chromium 3+. And what we want to do is we wanted to take that chromium 3+, by the way, which will be the hexaaqua. Yeah, we want to take that hexaaqua chromium 3+, and I want to oxidize it. I want to oxidize it to the dichromate ion, like that. Okay, so the way I'm going to do this is I'm going to use. What you need to do, guys, is you need to just learn these for transition metals. So we're starting off with chromium in a +3, and we're raising it to chromium +6. To do that, we use hydrogen peroxide as the oxidizing agent, and hydrogen peroxide and sodium hydroxide and NaOH. The condition is alkali. Alkali conditions. Condition, alkali. So if you want to raise the oxidation number of a transition metal, that's how you do it. Okay, now we've got to +6. What I want to now do is I want to take it back down to +2. Let's bring it down to chromium 2+. So now what we're trying to do is we're going to try and reduce it to the chromium hexaaqua 2+. I want to see the blue color. 2. Right, so now what I'm going to do is I'm going to add a reducing agent, which is what the H in capital letters stands for. The reducing agent for transition metals is zinc and HCl, the opposite condition. Condition, acidic. That's the one, and it'll go all the way down to 2 and stop. So that's all you actually need to know, is to learn those 2 things. By the way, trying to do the equations is a nightmare. I can try and show you those. They're very rare because they're A*. But just to show you, so for example, let's make it slightly easier. Let's go from the chromium 3+ hexaaqua to the chromium 2+ hexaaqua. Right, we're going to reduce it. Right, so the first thing we need to do is, this is a half equation. Yeah, so we need to balance for atoms, balance for charge. Now, the atoms actually all balance. All we need to do is adjust for charge. So all I need to do is give that 1 electron. Right, now, where am I going to get that electron from? I was reducing it, so this is from zinc. So the zinc is going to go down to zinc 2+ and give me 2 electrons. Right. So at this point, I can, by the way, it doesn't even look like it should be in acidic conditions, but it does need to be in reality. Now I'm going to double that equation to give me 2 electrons. They're on opposite sides. They cancel with those, and that now combines together. So 2 chromium hexaaqua 3 pluses will react with 1 zinc to form zinc 2 plus 2 chromium hexaaqua 2 pluses. There we go. I know I said they're horrible, but yeah, I'll give you some examples in the real homework that we can then use and go through. But guys, you need to know those 2 things. This is a nota bene. Learn these guys. Yeah, 1 oxidizes, 1 reduces. You need to know those. Just to quickly put those on top. Oil rig, oxidation is loss, reduction is gain. Yeah, this is oxidation, this is reduction. Learn them, you need them. Right, that brings me to the end of copper, folks. Check that out. Chromium is done. Who needs that? Right, I can go back to my channel. Right. Oh, I didn't turn my camera off. I totally forgot. Right, guys, I'm going to leave you guys be for now. I'll add the chromium homework to the classroom, guys, so you can have a look at, and I will see you guys next lesson. I'll see you tomorrow. See you later, guys.